Hello, this is Richard Hammack's Calculus 1 course. We are in part 4 of the course on applications of derivatives. In lectures 38A and B, we'll talk about a very useful application, a rule called LHopitals Rule that quickly and efficiently evaluates certain kinds of limits. This rule is named after a French mathematician shown here, and he, as you can see, had a very long name, but we're just going to call him L'Hopital. He has the distinction of having written the first calculus textbook. He didn't really invent the rule that bears his name, but he wrote about it. His rule, which we'll talk about today, gives a means of evaluating limits. So our plan is to apply derivatives to the problem of computing limits. And I want to talk about a typical type of limit that you've seen over and over and over again. Most of the limits we've dealt with have been of the form limit as x goes to c of f of x over g of x, where the limit as x approaches c of f of x is 0, and the limit as x approaches c of g of x is 0. So in this limit, you're getting 0 divided by 0. And our usual strategy for evaluation of such limits is to cancel the terms that are creating the 0 divided by 0. You know, we usually try to factor the top and the bottom and hope something would cancel. And for the most part, we were very successful in doing that. But that's partly because we were just looking at limits for which that was possible. You might ask the question, what if this is not possible? What if there's nothing in the f of x or g of x that you could cancel to get rid of that 0 divided by 0? So we're going to address that topic today. We're going to talk about two things. First of all, sort of the problems, what are called indeterminate forms. And these are problematic expressions such as 0 divided by 0, which we were getting in the limit up here. And then the next thing we're going to talk about is L'Hopital's rule, which is a method for evaluating such limits that have indeterminate forms. So let's jump right in, and we'll talk about indeterminate forms first. And I'm going to introduce this with a bunch of examples. Sort of some case studies, if you will. Think about the limit as x approaches 0 of sine x over x, which we know is equal to 1. In this limit, as x goes to 0, the numerator sine of x is approaching 0, and the denominator x is also approaching 0. So this limit has the form of 0 divided by 0. The top and bottom are both approaching 0, but the limit is equal to 1. Here's another limit, and I've tried to make this one as simple as possible. The limit as x approaches 2 of 3 times x minus 2 divided by x minus 2. You can see right off the bat that the x minus 2's cancel and gives you an answer of 3. But let's evaluate what's happening in this limit. X is approaching 2, so the denominator is approaching 0, but notice the numerator has an x minus 2 in it. So 3 times that is approaching 0 as well. So this limit has the form 0 divided by 0 as x approaches 2. Both top and bottom are getting closer and closer to 0. And the limit is equal to 3. So we're going to say that these two limits are of the form 0 divided by 0. Top and bottom are both approaching 0 in these two limits, but you'll notice that you get different answers, 1 and 3. And you could imagine for other limits of form 0 divided by 0, you might get answers different from those. So this 0 divided by 0 is going to be called an indeterminate form. It doesn't make any sense by itself, but limits having that form can make sense and equal different numbers. Some more examples. Here's the limit as x approaches infinity of 4x plus 2 divided by x plus 5, and it equals 4. because if you look at the highest power of x, its coefficient is 4 here, it's 1 down there. So you know the answer is going to be 4 divided by 1 from some chapter 2 techniques. So it's an easy limit to compute. But notice here that the 4x plus 2 and the x plus 5, they're both approaching infinity. So we would say that this limit has form infinity divided by infinity. And here's another one. Look at the limit as x approaches 0 of 1 over x divided by 2 over x. Well, if you reciprocate the 2 over x on the bottom and multiply it times the top, the x's cancel and you just get 1/2. So very clearly this limit equals 1/2. However, if you analyze what happens in the numerator and the denominator, as x goes to 0, the 1 over x approaches infinity and the 2 over x approaches infinity. So this limit has the form of infinity on top divided by infinity on the bottom. So we're going to say that these two limits are of the form infinity over infinity. And we're going to call that infinity over infinity an indeterminate form. By itself, it doesn't make any sense, infinity over infinity. But you could have different limits that both have that form and equal different numbers. So in a certain sense, infinity divided by infinity is meaningful. So what's happening if you look at, say, this first limit, both the 4x plus 2 and the x plus 5, they're both approaching infinity. But roughly speaking, the number on top is always 4 times bigger, or close to 4 times bigger as the bottom. So as x goes to infinity, the 2 and the 5 give less and less of a contribution compared to the 4x and the x. So roughly speaking, the top here, although it's approaching infinity, just like the bottom, is 4 times bigger than the bottom. So in the limit, you're getting 4. What else could we have? Well, here's an interesting limit. It's the limit as x goes to 0 of 2 times x times 1 over x, and clearly that's equal to 2. And here's another limit. The limit as x approaches pi over 2 of cosine of x times tangent of x equals 1. Now, these two limits look very different, but they have a basic common form. In this first limit, the 2 times x is getting closer and closer to 0, where the 1 over x, as x approaches 0, is approaching infinity. So this limit has the form of 0 times infinity, and it equals 2. In this second limit, down here, as x goes to pi over 2, the cosine of x is approaching cosine of pi over 2, which is 0, and the tangent of x is approaching, well, as x goes to pi over 2, tangent of x is going to infinity. So this limit has the form infinity times infinity. Now, tangent x is sine x over cosine x, so the cosines cancel. So this simplifies to the limit as x goes to pi over 2 of sine of x, and you can see that that's equal to 1. But the thing that's important here is that the form that these two limits have is 0 times infinity. And in the first one, you got 2, and the second one, you've got 1. So 0 times infinity is going to be called an indeterminate form. By itself, it doesn't make any sense whatsoever. What is 0 times infinity? It doesn't make sense. However, you're going to have limits like this one and this one that have the form of 0 times infinity, and they actually equal concrete numbers. So the expressions 0 over 0, infinity over infinity, and 0 times infinity are called indeterminate forms. By themselves, they're meaningless, but meaningful limits may have such forms, as we've seen here. Be careful not to confuse these indeterminate forms with forms that are not indeterminate. For example, if you ever had something of the form 0 divided by infinity, that's not indeterminate. It's flat out equal to 0. If in a limit the top is approaching 0 and the bottom is approaching infinity, the top is getting smaller and smaller and the bottom is getting bigger and bigger and bigger, so the quotient is getting smaller and smaller and smaller, getting closer and closer to 0. So a limit of that form equals 0. And in fact, you've seen many examples of such limits way back in part 2 of the course. Today we're concerned with limits of indeterminate form. And I can now tell you the rule that we'll talk about today, the main topic of today's lecture, that evaluates such limits. It's called LHopitals Rule, and it's capable of evaluating a limit of indeterminate form, either 0 over 0 or infinity over infinity. And here's how it works. If the limit as x approaches c of f of x over g of x has indeterminate form 0 over 0 or infinity over infinity, then this limit, the limit as x approaches c of f of x over g of x, is equal to a different limit, the limit as x approaches c of f prime of x over g prime of x. That's LHopitals Rule. Let me give you an example of how this rule could work. And in this example, we'll look at a limit that we already know. The limit as x approaches 0 of sine x over x. We know that's equal to 1. But in this example, we will apply LHopitals Rule to it to get that answer of 1. In looking at this limit, the limit as x goes to 0 of sine x over x, notice the numerator, sine of x, is getting closer and closer to sine of 0, which is 0. And certainly the bottom, x, is getting closer and closer to 0. So this is a limit of indeterminate form 0 divided by 0. And LHopitals Rule says that given such a limit of indeterminate form 0 over 0, it's going to be equal to the limit as x approaches c of the derivative of the top divided by the derivative of the bottom. So let's apply LHopitals Rule here. And this LH just stands for LHopitals Rule. It means we're applying it and going from here to here, from here to here. So in LHopitals Rule, to get the limit as x approaches c of f of x over g of x, it's equal to the limit as x approaches c of f prime of x over g prime of x. In our case, that would be the limit as x approaches 0 of the derivative of sine of x over the derivative of x. Working out those two derivatives, we get the limit as x approaches 0 of cosine x divided by 1. And this is a really easy limit to work out. It's not an indeterminate form. To get it, we can just apply a limit law, let x go to 0 on the top and also on the bottom, and you get cosine of 0 over 1, which equals 1. So in this example, we applied LHopitals Rule to get an answer of 1. And we know that's right because we've seen this limit before and we worked it out by other means. With this example, I think you can see why LHopitals Rule is so powerful and so useful. And it's this. Very often in taking derivatives, a function will get simpler. For example, the derivative of x turns into 1. And in this step right here, when the derivative of x was 1, suddenly the denominator is not approaching 0 anymore. And we get a much simpler limit. So in LHopitals Rule, given a limit like this one of indeterminate form, you transfer it to a potentially simpler limit that may not have an indeterminate form. And that's very powerful. So I've restated LHopitals Rule up at the top. Now, real quickly, before we look at the other examples, I want to just give an informal justification of why you should believe this. The text gives you some explanation, but I want to say a few words about it now. A few words about an informal justification of why you would expect that these two things are equal. Now, let's say that we're dealing with 0 divided by 0. Say the limit as x approaches c of f of x divided by g of x has form 0 divided by 0. Now, what that would mean is that the limit as x approaches c of the f of x on the top equals 0, and also the limit as x approaches c of g of x on the bottom is equal to 0. Now, let's assume that everything inside is continuous. Now, this is why this is just an informal justification. This is an assumption that is going to break down in some cases. But what I'm trying to do is just give you an informal justification for why this rule works. So let's assume everything is nice and continuous. And that would mean that f of c is equal to 0. Remember, if f is continuous, then the limit as x approaches c of f of x, it has to equal f of c, which is also 0. So likewise, you'd get g of c equals 0. And now let's look at this limit as x approaches c of f of x over g of x, and we want to convince ourselves that it's equal to this, the one with the derivatives. So the first thing we're going to do is we're going to subtract a c, f of c from the top and a g of c from the bottom. And remember that f of c and g of c, they're just equal to 0. So when we're subtracting the f of c from the top, it's really the same as the top here. And likewise, the g of x on the bottom that we started with becomes g of x minus 0. So we haven't changed anything in going from here to there. Those two things are equal. But I'm going to break this limit up into two parts by introducing an x minus c on the bottom here and on the top there. And those two terms would cancel each other out and give you what you had over here. So why do we have them there? Well, look at just this little piece right there. The limit as x approaches c of f of x minus f of c divided by x minus c. You'll recognize that as one of our definitions for f prime of c. And this one, g prime of c, should be the limit as x goes to c of g of x minus g of c over x minus c. This would be the reciprocal of g prime of c. So what we're getting here in this limit is f prime of c times 1 over g prime of c. F prime of c divided by g prime of c. And the f prime of c would be the limit as x goes to c of f prime of x, and the g prime of c on the bottom would be the limit as x goes to c of g prime of x. Now here I'm using the fact that everything's continuous and going from here to here, so that f prime of c is the limit as x approaches c of f prime of x. But what we get here is that the limit as x approaches c of f of x divided by g of x equals the limit as x approaches c of f prime of x divided by g prime of x, which is what LHopitals Rule states. So this should give you a sense for why this rule, LHopitals Rule, is true. And again, this is not a proof. This argument's got some holes in it. And you could tighten this up into a proof if you wanted to. And we haven't even addressed infinity over infinity. But if you want some better justification, you're free to look this up, find a proof of LHopitals Rule. For the most part, as we go on, we're just going to accept LHopitals Rule on faith. That every time we have a limit that has indeterminate form 0 divided by 0 or infinity divided by infinity, then that limit can be got this way. Let's look at some examples. The limit as x approaches 1 of 1 minus cosine x minus 1, whole thing divided by x squared plus x minus 2. If you look at this, x is approaching 1, so the cosine x minus 1 should be approaching cosine 1 minus 1, which is cosine 0, which is 1. So you have on top something approaching 1 minus 1, so the top is approaching 0. The bottom is approaching 1 squared plus 1 minus 2, so that's approaching 0 as well. So if you look at this limit, it has form 0 divided by 0. So this is something that LHopitals Rule would apply to. And LHopitals Rule would say that this limit is equal to the limit as x approaches 1 of, on top, the derivative of what was on top over here, and on the bottom, the derivative of what we had here on the bottom. So the derivative of x squared plus x minus 2 is 2x plus 1. The derivative of 1 minus cosine x minus 1 would just be sine of x minus 1. Remember, here we're using the chain rule. The derivative of minus sine is minus, the derivative of minus cosine is minus sine of x minus 1 times the derivative of x minus 1, and that's just sine of x minus 1. So in just one step with LHopitals Rule, notice how we have simplified things. A lot of terms dropped out. And in fact, this limit is no longer an indeterminate form. And the denominator is not approaching 0 anymore, so you just plug in the 1 to the top and the bottom, and we get sine 0 divided by 2 times 1 plus 1, and that's sine of 0 is equal to 0, so this limit equals 0. So that's what this section is all about, evaluating complicated limits with this new technique called LHopitals Rule. And you'll notice that in this limit, I don't know that we could have evaluated that with techniques from Chapter 2. But here we got it very quickly with LHopitals Rule. Here's another example. Limit as x approaches 0 of the square root of 1 plus x minus 1 minus x minus 2, whole thing divided by x squared. So x is approaching 0, so the x squared on the bottom is approaching 0. And let's see, on top we're getting square root of 1 plus 0 minus 1 minus 0 over 2. That's 0 as well on the top. So this limit has form 0 divided by 0. So it's something that LHopitals Rule would apply to. And let's apply LHopitals Rule. And again, the little LH means L'Hopital. We've just applied his rule right there. So the x squared on the bottom turns into its derivative 2x. Now, if you think about it, the square root of 1 plus x minus 1 minus x minus over 2, here's its derivative. The 1 dropped out. The 1/2 x turned into just a 1/2. So we get a somewhat simpler looking limit. But if you look at this limit that we got, x is approaching 0. So the 2 times x is approaching 0 on the bottom. And on top, we get 1/2, 1 plus 0 to the power of minus 1/2, which is just 1/2, minus a half. We still have form 0 over 0. So although we've simplified things a little bit, we cut some powers down, we still have form 0 over 0. And how are we going to evaluate that? Well, since it's still form 0 divided by 0, we could use L'Hopital's rule again. Let's see what we get. Using L'Hopital's rule a second time, the derivative of the 2 times x becomes just a plain old 2. And over here, the negative 1/2, that drops out. Its derivative is 0. You take the derivative of this part, and you get that. So we have the limit as x approaches 0 of negative 1/4 times 1 plus x to the power of minus 3/2, all divided by 2. And the beauty of this is that's no longer an indeterminate form. In fact, the bottom is a 2. So you're not getting the problem of anything on the bottom turning into 0. And it looks like we could just plug in x equals 0 here. And doing so, we have negative 1/4 times 1 plus 0 to the power of minus 3/2. So that's negative 1/4 times 1 to the power of minus 3/2. So that's negative 1/4 on the top divided by 2. It's equal to 1/8. So there we go, 1/8. And I'll remind you that if we were just looking at what we had available to us in Chapter 2, I don't think we could solve this limit. It wouldn't be one of the exercises in Chapter 2 because you can't do it with those techniques. But with this high-powered tech of L'Hopital's rule applied twice, we get down to an answer of negative 1/8. This limit is equal to negative 1/8. New example. Limit as x approaches pi over 2 of 2 plus secant x divided by 3 tangent x. Now let's look at that. X is approaching pi over 2. So remember, tangent of x has an asymptote at pi over 2, a vertical asymptote. So as x goes to pi over 2, tangent of x is approaching infinity, either positive infinity or minus infinity, depending on which side of pi over 2 x is approaching. And also the secant x, as x goes to pi over 2, that goes to infinity as well, and then plus the 2. So this has the form infinity divided by infinity. It's a limit of an indeterminate form. Now remember that L'Hopital's rule applies to limits of indeterminate form infinity over infinity. So we should be able to apply it here. So L'Hopital's rule, if we apply it, says we should get the limit as x approaches pi over 2 of the derivative of the top, which is secant x tangent x, divided by the derivative of what's on the bottom here, which is 3 secant squared x. Now, when you're working these problems and you do a step like this where you've applied L'Hopital's rule, one of the first things you could do, you should always do is, if you can, clean up and simplify. We've got a secant x divided by a secant squared x here. So let's do that cancellation. We get the limit as x approaches pi over 2 of tangent x over 3 secant x. And let's examine what's happening there. The tangent of x is sine x over cosine x. The 3 secant x is 3 divided by cosine of x, because secant x is 1 over cosine x. And we get some simplification here, reciprocating the bottom and multiplying times the top gives us just a sine of x over 3. So we have the limit as x approaches pi over 2 of sine of x over 3. And that's equal to 1/3 because the sine of pi over 2 is 1 divided by 3. So you get 1/3 as the value of this limit. Some more examples. And these few examples we'll do on this slide, they're going to involve the function f of x equals e to the x. So let me just remind you of what that looks like. Remember, as x goes to negative infinity, e to the x goes to 0, reflected in this horizontal asymptote right here. Okay, we have the limit as x approaches infinity of e to the x divided by 1 plus e to the x. What would that be? Well, x is going to infinity, so on top, e to the x is approaching infinity too, and 1 plus e to the x is approaching infinity. So this limit has form infinity divided by infinity. So we should be able to apply L'Hopital's rule to that. L'Hopital's rule says the limit as x goes to infinity of e to the x divided by 1 plus e to the x is equal to the limit as x goes to infinity of the derivative of e to the x, which is e to the x, divided by the derivative of 1 plus e to the x, which is also e to the x. And look at that, it's really beautiful because e to the x divided by e to the x is 1. So right away we get that the limit equals 1. Just a quick application of L'Hopital's rule and a quick simplification gave you the answer to this. Okay, number 5, it looks almost the same as number 4, except the powers of e, instead of being to the power of x, are both to the power of negative x. So what's happening here? Well, x is going to infinity, and then we have e to the power of negative x. Well, x is getting to be a bigger and bigger and bigger and bigger positive number. So here you have e to a really big negative number. And remember, that's a really small number. So the numerator is going to 0. And what about the denominator? 1 plus a really small number. So this has form 0 divided by 1. Now, actually, that's not even an indeterminate form. LHopitals rule would not apply to this problem because this limit is not an indeterminate form. It has form 0 divided by 1. And that's something that you can just use old-fashioned limit laws for from way back in chapter 2. You have the limit as x goes to infinity of this f of x divided by g of x. You take the limit of f of the top function divided by the limit as x goes to infinity of the bottom function and work those out separately. You get 0 divided by 1 plus 0 equals 0. So the moral of this problem is to watch out, because don't get on automatic pilot, because not every limit you work out is going to involve an indeterminate form. And if you don't have infinity over infinity or 0 divided by 0, then LHopitals rule is not going to apply, and use some other techniques. This limit that we just did, number 5, we could have done that one way back in like the second section of chapter 2. Way back then. You don't need LHopitals rule for that. In fact, LHopitals rule doesn't even apply. Okay, we're moving on here. I want to talk about a new type of indeterminate form. Remember, at the beginning of today's lecture, we said that, well, there are 7 indeterminate forms. The 2 that LHopitals rule applies to are 0 divided by 0 and infinity divided by infinity. But we also noted that 0 times infinity was an indeterminate form. And I want to talk about how to handle that. Now, in the examples we're going to look at in just a moment, they'll involve the function ln of x. So remember what ln of x looks like. It looks like this. It has an x-intercept of 1, and as x goes to 0 from the right, ln of x goes to negative infinity. And I'll just put that right here for your convenience, just as a reference. Limit as x goes to 0 from the right of ln of x equals negative infinity. Okay, continuing our examples, we're at number 6. Limit as x approaches 0 from the right of x times ln of x. Now, look at that. The x right here is approaching 0, but the ln of x is approaching negative infinity. So we would say that this limit has form 0 times infinity. So it's tempting to say that the answer is going to be 0, because shouldn't 0 times anything be 0? Well, let's find out. This limit, as x goes to 0 from the right, x times ln x, which has form 0 times infinity, is not one of the forms that LHopitals rule applies to. Remember, LHopitals rule only applies to 0 divided by 0 or infinity divided by infinity. So you can't apply LHopitals rule to this limit. But here's our technique for dealing with limits of the form 0 times infinity. We're going to convert them to 0 divided by 0 or infinity divided by infinity. And here's how we're going to do it. We can take this x right here down to the bottom under the ln x by reciprocating it. So you have 1 over ln of x divided by 1 over x. Now, if you reciprocate the 1 over x, the quotient at the bottom, multiply times the top, that just boils back down to x times ln of x. So these two limits they're really the same limit. They're exactly the same limit. There's just a slight change in the way, sort of a superficial change in the way we've expressed it. brought the x down to the bottom as a 1 over x. But in this new limit that's equal to the previous one, look at the form it has. You have x goes to 0 from the right, so the ln of x is approaching infinity. And also as x goes to 0, the 1 over x is approaching infinity too. So this limit has the form of infinity over infinity. And that's something that LHopitals Rule will apply to. So I'm going to pause right here and just point out that every time we have an indeterminate form of 0 times infinity, we'll just take one of those two factors and bring it down to the bottom as its reciprocal. And that's going to convert it to either infinity over infinity as it did here, or maybe 0 divided by 0, as we'll see in just a second. But let's continue with this. We're working out this limit. It's form infinity divided by infinity, so that's something LHopitals Rule would apply to. And let's apply LHopitals Rule. So we do the derivative on the top, and on the bottom we have the derivative of the 1 over x. It's a minus 1 over x squared. So by LHopitals Rule, this becomes the limit as x goes to infinity, 1 over x divided by negative 1 over x squared. Now let's simplify. You reciprocate the bottom and multiply by the top, and that just gives you a negative x. We got the limit as x goes to 0 from the right of negative x, and that gives you 0. So there we go. The limit as x goes to infinity of x times ln of x equals 0. Whenever you're doing this trick where you convert a 0 times infinity to something that LHopitals Rule would apply to, as we did here, you have a choice. Do you want to bring the x down to the bottom or the ln of x down to the bottom as its reciprocal? And you can do either one of those. Let's do this exact same problem again, a slightly different way. Suppose that we had the limit as x goes to 0 from the right of x times ln of x, which is exactly the same limit that we just did. And you look at that and you go, oh, it's 0 times infinity, so I need to convert that to a fraction so I can apply LHopitals Rule. One option would be to bring the ln of x down to the bottom as its reciprocal. And look at that for just a moment. X divided by 1 over ln of x, it equals x ln x. So these two limits are equal to each other. But if you look at this one, the x on the top is approaching 0. And what about the 1 over ln x? Well, x is going to 0 from the right. So the ln of x on the way down here is going to infinity, getting bigger and bigger. So the reciprocal of that is getting smaller and smaller. So this limit has the form 0 divided by 0. So that's something that we could apply LHopitals Rule to. And notice that in the previous way we solved this, we got infinity divided by infinity. Bringing the other term, the one that was going to infinity, down to the bottom as a reciprocal, that's going to give you form 0 divided by 0. Either way, we can apply LHopitals Rule to this. So in applying LHopitals Rule, the x turns into its derivative. The 1 over ln of x turns into its derivative. And there, let's see, you could use either the quotient rule or the generalized power rule. Either way, you might want to pause the video and work out the derivative of 1 over ln of x and check that you do get negative 1 over ln of x squared times x. So we have this new limit, which looks kind of complicated, but it's 1 over a fraction, so we could reciprocate, and we get the limit as x approaches 0 from the right of negative x ln of x whole thing squared. Now, if you look at that, that's even more, it's very similar, but more complicated than what we started with. It's like putting a negative in front of this and squaring the ln of x. And if we couldn't work out this limit, that was our initial problem, we've moved on to one that's even more complicated. So in a certain sense, this is circular. You're not getting to a simpler limit. You're getting to a more complicated limit. So whenever in L'Hopital's rule you're doing this and you get to something circular like that, just stop. Okay. What this means is that you would have been better off, better served by solving this limit the first way we did it, bringing the x down. Now, it's very important to practice a lot of these problems because you'll find yourself in a situation where you're working out an indeterminate form like 0 times infinity, and you want to always look a couple of steps ahead and ask yourself, well, what am I going to bring down to the bottom? The x is a 1 over x, or the ln x is a 1 over ln x? And you should always be thinking about, well, what's going to give you the simpler derivative? And sort of go for that. But if you ever get to a point where it becomes circular, as it was in this problem, try it the other way. All of the problems in this book and the exercises, they're going to work out neatly, but sometimes if you take a wrong approach, it's going to get impossible. And be prepared for that. If you work a lot of these problems, you're going to become very good at them very quickly, and you'll start to be able to look a few steps ahead. Let's do another example of the form 0 times infinity. Here we have the limit as x goes to pi over 2, 2x minus pi times secant x. Now if you look at that, x is approaching pi over 2, so the 2x minus pi is getting closer and closer to 0. But we know as x goes to pi over 2, secant x approaches infinity, either positive infinity or negative infinity, depending on how x is approaching. So this limit has form 0 times infinity. So we've already talked about on the previous slide a way to solve limits like this. You're going to convert them to a form 0 divided by 0 or infinity divided by infinity. You can either bring the 2x minus pi down to the bottom with its reciprocal, or the secant down to the bottom with its reciprocal. Which of those two options will we do? Well, think about how you're going to apply L'Hopital's rule. It's going to involve a derivative on top and a derivative on the bottom, and you want to do this so that things simplify. And I would much rather take the derivative of 2x minus pi, which equals 2, than I would the derivative of its reciprocal. So that tells me, hey, let's leave the 2x minus pi up on top and then bring the secant x down to the bottom as its reciprocal, like this. So you get the limit as x approaches pi over 2 of 2x minus pi, whole thing divided by the reciprocal of secant x. And again, of course, this simplifies back to that, so they're equal. We could do another simplification because 1 over secant x is cosine of x. So we get the limit as x approaches pi over 2, 2x minus pi divided by cosine of x. Now there, the numerator is approaching 2 times pi over 2 minus pi, that's 0, and the denominator is approaching cosine of pi over 2, which is 0. So this has form 0 divided by 0. See, we converted this limit of form 0 times infinity to form 0 divided by 0. And this is something that L'Hopital's rule will apply to. And applying L'Hopital's rule, we take the derivative on the top, divided by the derivative of what the bottom is, and take the same limit. We get the limit as x approaches pi over 2 of 2 over minus sine of x. And this is beautiful because x is going to pi over 2, so sine of x is approaching sine of pi over 2, and that's not 0. Just plug things in. So we get 2 over minus sine of pi over 2, which just equals negative 2. So we've successfully evaluated the limit as x approaches pi over 2, 2x minus pi secant x. It equals minus 2. I want to do this exact same problem by the other way, by bringing the 2x minus pi down to the bottom as its reciprocal. And looking ahead, instead of form 0 over 0, that should give us a form infinity over infinity, but L'Hopital's rule can handle that too. Let's see how that would work. So we've got this limit of form 0 times infinity, same exact limit that we just looked at, but we'll try something a little bit different. This time the 2x minus pi, we're going to bring that down to the bottom as its reciprocal. And now that's form infinity divided by infinity, because as x goes to pi over 2, secant x is approaching infinity. And the 1 over 2x minus pi, the denominator there is getting closer and closer to 0, so that reciprocal is going to infinity. So we have form infinity divided by infinity. So we can apply L'Hopital's rule here. So that involves the same limit, but the secant x turns into its derivative, and the 1 over 2 minus x turns into its derivative. Here I use the generalized power rule. But look at the limit that we got here. It's way more complicated than what we started with. Compared to this other approach, where we got a really simple limit really quickly, this one just seems to be getting worse and worse. It's a mess. So if ever you're working L'Hopital's rule with a problem like this, where you're converting a 0 times infinity to 0 over 0 or infinity over infinity, and you get a mess like that, well, that's a signal to go back and try it the other way. Bring the other term down to the bottom. Not the 2x minus 1 as we did here. That just led to a mess. Keep that 2x minus 1 up on the top. One more example. This example is intended to remind you that not every problem where you'll use L'Hopital's rule starts out as find this limit. In example 10, we want to find the horizontal asymptotes of the function f of x equals x e to the x. You'll remember to find the horizontal asymptotes of a function, you work out two limits. The limit as x goes to infinity of f of x, and the limit as x goes to negative infinity of f of x. And if in either case you get a finite number L, then the line y equals L is a horizontal asymptote of the function. So let's get to work on that. Let's first check out the limit as x goes to infinity of x e to the x. Well, this is easy. There's not much work involved here. X is going to the infinity, so e to the x is going to infinity as well, so their product is just getting bigger and bigger and bigger. So the limit as x goes to infinity of x e to the x equals infinity. Not a finite number. So there's no horizontal asymptote corresponding to this limit. But that doesn't necessarily mean there's no horizontal asymptote to this function. It could be that if we look at the limit as x goes to negative infinity of x e to the x, we don't get infinity, we get a finite number. So let's check that out. Take the limit as x goes to minus infinity of x e to the x and examine what's happening there. And we'll be pretty quick here in the interest of time. But you'll notice that this limit has the form of infinity times 0. X is going to negative infinity, so that's infinity, or a flavor of infinity. And e to the power of x, that's e to a very big negative power, so that's very close to 0. So this has form infinity times 0. So our trick for dealing with indeterminate forms of that type is to bring one of those factors down to the bottom. X has a simple derivative, so we're going to leave that by itself where it is. And we can bring down the e to the x as an e to the minus x. Looking at this limit, its form is infinity over infinity. X is going to negative infinity. On the bottom, e is being raised to the power of negative, a very big negative number. So that's e to a very big positive number. which is infinity, or going to infinity. So since we have the indeterminate form infinity over infinity here, we can apply L'Hopital's rule, and in so doing, the derivative of x is 1. For the derivative of e to the minus x, we've got to use the chain rule. That's e to the minus x times the derivative of minus x, which is negative e to the minus x. And let's bring that negative power back up to the top. We've got the limit as x goes to negative infinity of minus e to the x. X is going to minus infinity, so e to a very big negative power is very close to 0. So although minus e to the x is negative, it's getting closer and closer and closer to 0 the bigger x gets. Our limit equals 0. So from this we can conclude that the line y equals 0, which is the x-axis, is a horizontal asymptote. So we've answered our question. We're done with number 10, but just to underscore the answer here, this is a familiar function back when we were talking about the first and second derivative tests. Somewhere in there we actually graphed f of x equals e to the power of x. And I'll quickly remind you of what we got. We looked at where the derivative was positive or negative, and the second derivative was positive or negative. And we found out where this function was increasing and decreasing, where it's concave up and concave down. And the graph looks something like this. We had a local minimum here, an inflection point right there. And look at what's happening as x goes to minus infinity. F of x is indeed getting closer and closer and closer to 0. So the x-axis really is a horizontal asymptote for f of x. That's it for today. As a quick recap, we introduced L'Hopital's rule. It evaluates limits of indeterminate form in 0 over 0 and infinity over infinity. And using it, we can also evaluate limits of indeterminate form 0 times infinity. Next time, we're going to see that there are 4 other indeterminate forms: infinity minus infinity, 1 to the power of infinity, infinity to the power of 0, and 0 to the power of 0. And we'll see how we can use L'Hopital's rule to deal with those. For now, it's a good idea, I think, to get some practice. We're halfway through with L'Hopital's rule. I'll see you next time in Lecture 38B. Goodbye.